Good evening, ladies and gentlemen. Welcome to today's Science Symposium of 포항제철고 High School. My name is Yeji Moon, the moderator of today's discussion. And with me, there is Pan Sa-young and Ryung Seo to help moderate our panel today. Our distinguished panelists will share their insights, research findings, and recommendations about their mathematical and scientific knowledge. Before we start, let's hear a word from our principal who has made her precious time for us. And then we will have photo time all together with our math teacher, Mr. Kim.
오늘 이 귀한 시간에 여기에 모인 여러분들한테 나도 영어로 뭔가를 해야 될 것 같은데 그래서 가끔 영어를 쓰고 전체는 못 씁니다. 오프닝 뭔가 여러분들한테 멘트를 해야 될 것 같은데 오늘 이제 요 내용이 수학, 과학, 그리고 경제, 그리고 영어 이런 것들이 어떻게 뭉쳐져서 이 친구들이 어떻게 심포지움을 할까 참 다양한 주제인데 여기 하나 빠진 게 있었어요. 꼭 없습니다. 그래서 이걸 어떻게 스타트를 할까 하고 하다가 나는 꽃이라는 김춘수의 시를 가지고 시작을 하고 싶습니다. 사실은 오늘 여러분들의 이 프로그램의 순서를 보고 내가 지금부터 35년 전으로 나의 타임이 돌아갔어요. 왜냐하면 내가 이제 고려대학교 물리화학실에서 석사를 받은 그 논문이 무엇이었었냐면 초전도체 결정구조에 대한 논문이었는데 그게 앞에 이제 보니까 제 1번 주제로 나와 있었고 그때 내가 석사했을 때 양자역학을 배웠었는데 슈레딩거의 파동 방정식 해밀토니안 해를 구하는 걸 했었어요. 직접 수학 문제를 풀었습니다. 그래서 나의 시간이 잠깐 동안 35년 전에 내 대학원에 그 시절로 돌아갔었어요. 그 시간을 여러분들이 소환해 준 거에 대해서 너무 고맙게 생각하고 이런 일들이 어떻게 일어날 수 있을까? 김춘수의 꽃을 여러분들에게 한번 읽어주면서 나의 오프닝 멘트를 하고자 합니다. 꽃, 김춘수. 내가 그의 이름을 불러주기 전에는 그는 다만 하나의 몸짓에 지나지 않았다. 내가 그의 이름을 불러주었을 때 그는 나에게로 와서 꽃이 되었다. 내가 그의 이름을 불러준 것처럼 나의 이 빛깔과 향기에 알맞은 누가 나의 이름을 불러다오. 그에게로 가서 다시 나도 그의 꽃이 되고 싶다. 우리들은 모두 무엇이 되고 싶다. 나는 너에게, 너는 나에게 잊혀지지 않는 하나의 눈짓이 되고 싶다. 우리가 이 밤에 여기 이 자리에 모여서 우리는 무엇을 하려고 할까요? 어떤 사람들은 아마 그렇게 얘기할 수도 있어요. 그거 다 쓸데없는 짓이야. 너네 왜 시간 낭비해? 저는 거기에 대한 답을 바로 이 시로 해주고 싶습니다. 여기에 참여하지 않은 사람들은 이 의미를 모릅니다. 우리가 수학과 과학과 경제와 영어와 이 시를 연결해 보십시오. 그러면 여러분의 마음에 꽃이 피어날 거고 그 꽃은 여러분 각자의 자기가 가진 스토리를 하나를 더 여러분의 인생에 추가해 줄 것입니다. 이것의 의미는 여러분이 각자 해석하십시오. 이상입니다.
Thank you very much, Jung-min Kim, and on behalf of all the panelists, I want to thank you for your kind words. We hope we do a great job here today with this panel. Also, I'd like to have the audience engaged fully in the discussion. So your comments, advice, or any other input would be appreciated as we go along with the session. The objective of this panel will be to provide you through different presentations on in-depth exploration related to career paths based on mathematics. Afterwards, as I said before, hopefully we'll get a lot of questions and even be able to answer them. To kick off the opening ceremony, we have our executives Kim Jung-min, Ryung Seo, and Oh Yoo-jin with us to give their opening address. Please give a big welcome to our first speakers.
everyone, I'm Yujino. I'm Ryuhyang-seok.
I'm Jungmin Kim.
And we're going to talk about quasi-crystals. I will divide my presentation into 6 parts like this. Please look at this presentation. And first of all, I'm going to introduce quasi-crystal and crystal's definition. Crystal has a structure in which atoms are arranged periodically, but quasi-crystals are arranged aperiodically. Let's find out structure and characteristic. It has no spatial periodicity and rotational symmetry. It also follows the Fibonacci sequence and the Green lattice. And it has very low surface energy and friction. Let's look about applicability of quasi-crystals. It has high intensive forming coating and other new materials such as making golf clubs or diesel engines can be used. It also used as external materials for electronic devices such as mobile phones due to their excellent strength and vibration absorption, and are used in new semi-crystalline materials such as alloy engine with new characteristics or converting heat of insulation into electricity. Finally, let's learn about Penrose tunneling. Penrose tunneling is a mathematical proof which cannot fill a plane with a pentagon of the same size, but fills a plane with 2 figures. Before explaining more about Penrose tunneling, we first learn about periodic and aperiodic tunneling. Periodic tunneling means that flat surface can be covered perfectly without gaps, and patterns can only be continued through movement without rotation or flipping after replicating some of the tiles. Aperiodic tunneling means that non-periodic tiles fill the plane. And then, what is the minimum number of tiles required for aperiodic tunneling? We can answer this question with this proof. Start with a pentagon. Adding another pentagon to the surrounding, we notice that the gap and the entire shape of it were pentagonal. After that, split pentagons into smaller pentagons. The conjoining pentagons are connected in a lumbar shape. Fill the empty space, and we're going to divide the smaller pentagons. This is the result. And we can notice that 5 times symmetry allows aperiodic plane tunneling. To make proof simpler is a second proof. The first green one is a kite, and the red one is dirt. So we can ensure a single tile can only tile plane aperiodically.
Now we will talk about development of polyhedral curved surface, starting with the ignition equation of the Fibonacci sequence. Let's say the ignition equation of the Fibonacci sequence is an plus 2 equals an plus 1 plus an. If this is extended to the general equation and the relationship between roots and coefficients are used, 2 square of x equals x plus 1. Now 2 square of x minus 1 equals 0, and p times 2 square of x plus q times x plus r equals 0. So we can see that p equals 1, q equals minus 1, and r equals minus 1. Alpha plus beta equals minus q, and alpha times beta equals r. A1 equals 1, and A2 is 1. Now we can see that alpha plus beta equals 1, and alpha times beta equals minus 1. We can find the general term of the Fibonacci sequence by creating a repetitive form and substituting it into the general form after solving the system of equations. Now the value becomes an, which is 1 over root 5 times n square of 1 plus root 5 over 2 minus n square of 1 minus root 5 over 2. The ratio expression is an plus 1 equals n plus 1 square of beta minus n plus 1 square of alpha over beta minus alpha. Now we can see an plus 1 over an equals beta minus alpha times n square of alpha over beta over 1 minus n square of alpha over beta. If we put a limit on this value, it converges to 0. As we can see, beta equals 1 plus root 5 over 2, and the value of alpha is 1 minus root 5 over 2. Beta is bigger than alpha, so limiting n to infinity on n squared of alpha over beta, it converges to 0. The ratio of the Fibonacci sequence is 1 plus root 5 over 2. The diffraction pattern of this quasi-crystal structure is the golden ratio, which is 1.618. And this is the same value as 2 cosine pi over 5. The Penrose tiling has a lot to do with this. The method using this property is a section method of obtaining a quasi-crystal structure from a grating that is periodically decorated at a higher level. Now we'll talk about polyhedral fabrication. If the part shown through the two types of rhombus is shown using a bird's eye view as shown in the figure next to it, it can be seen that the two types of rhombus appear as one, and the same rhombus on the plane. These rhombus have the same length and a reference angle is different. Two rhombus are based on an acute angle and one on an obtuse angle. The basic form of the stereoscopic form of the quasi-crystal structure system represents the form of a hexahedron represented using these two types of rhombus, with different angular character at the basic element. All sides of this hexahedron represented at the basic form of the quasi-crystal system are formed of the same rhombus. In addition, the shape of this hexahedron is the same rhombus shape on all sides, but the shape of the two hexahedrons varies due to the difference in the reference angle. The two hexahedrons presented at the basic elements of the quasi-crystal system are combined to produce a pentahedron and an icosahedron. An icosahedron is manufactured using 5 hexahedrons each. A 30-sided body is manufactured using 10 hexahedrons each. You can start at this icosahedron.
Today, I'd like to talk about an exciting new discovery from the world of tiling theory. Recently, it was announced in this March, a team of mathematicians discovered something remarkable known as an aperiodic monotile. Here's the one, an aperiodic monotile. So today, I'd like to walk you through what this thesis means and show you two really cool proofs. How do we know an aperiodic tiling doesn't repeat? If you look at any given tile, we can tell by its orientation relative to all its neighbors, which larger trapezoid it belongs to, and the tile's position within it. The big trapezoid is made of 4 small trapezoids. I'm going to number those trapezoids 1, 2, 3, and 4. Then take a look at the picture on the right side. The trapezoid that makes up the trapezoid in the center of orange area are numbered in 1, 2, 3, and 4. Then in the entire orange area, we can separate the area into 4 smaller trapezoids and number them as we did in the first step. Now look at the whole picture. Repeating the numbering steps will give us a sequence of numbers which tells us where this tile is within the larger structure. So we can get coordinates with the hierarchy, and any two tiles will have different coordinates since they're going to be in different places. If the pattern repeated, then there would be 2 tiles somewhere with the same sequence, since the sequence is determined by the orientation relative to the neighbors. And the neighbors will all look the same since the pattern is repeating. And that can happen since we said the coordinates are all different, so there can be a repeated pattern. A tiling like this never repeats is called aperiodic. Then a question pops up. Is it possible to find Einstein? Einstein, which means one stone in German, is a tile that only has aperiodic tiles. A few years back, this thing was discovered. All of these disconnected bits are part of the single tile. But that's kind of unsatisfying. I mean, it's really cool, but if you saw a tiling with this in the wild, you would think it used 3 different kinds of tiles, not just one. So what we really want is a connected aperiodic tile.
meet the head. When we tile the plane, it looks like this. It's a pretty pattern and it feels like there are some hints of structure there, but it doesn't look like it fits. So how can you prove it? As we did before, number the tiles and then we find different sequences. The argument has the same structure as most other proofs of aperiodicity. Find meta tiles, put them in a recursive hierarchy, and extract coordinates. So if that were all, this paper wouldn't have gotten mathematicians so excited. But the authors didn't stop there. They actually found a second proof. This one is very different from any that came before, and in the process, they found not just one, but an infinite family of aperiodic monotile. If you look at our head as a 13-sided polygon, we see that it has size of 3 distinct lengths, 1, 2, and root 3. And then, if we treat this side, length 2, as 2 sides of length 1, then really there are only 2 lengths we need to worry about, 1 and root 3. And if we vary those lengths, or more importantly, the ratio between them and keep the angles between neighboring sides the same, then we can get a whole family of shapes. So for example, if you shrink this green side to the same length as these brown ones, we end up with the shape here. And then if we stretch the brown side out to length root 3, we get this shape instead. At the extreme ends, if we shrink the brown side down to 0, we get this chevron shape. And if we shrink the green side to 0, we get this comet. So the head lies somewhere on a continuum between the chevron and the comet. We'll prove that every shape on this continuum, except for the endpoints, is also an aperiodic monotile. Suppose we have a tiling with these tiles. Let's say the head. Then we can get a corresponding tiling with chevrons and another comes with by shrinking the appropriate side to 0. To keep the density of the tiles constant, we'll need to keep their areas constant, which means we need to scale the size appropriately. And the size of the chevrons will come out to root 2 times the size of the comets. Since the size of each chevron are all the same length, and the angles between them are all multiples of 60 degrees, that means the chevrons fit into a triangular grid with side length root 2. And similarly, the comets will fit into a triangular grid with side length 1. If our tiling on this was periodic, then both the tiling with chevrons and comets would also need to be periodic. And because the density of tiles is the same, we must have the same distance between repeated parts. And since both of these tilings are on grid, the distance must be between 2 corresponding corners, that the lattice point on this grid, and also between 2 lattice points on this grid. But the distance between lattice points are different in the 2 grids. There is no distance that's the same in both, and there's no distance where the tilings can repeat, which means there's no simultaneous periodic tiling for the chevron and the comets. And thus, there's no periodic tiling for the head or any other tile on this continuum, which means we have a whole family of aperiodic monotiles. So now we've proven that the head is an aperiodic monotile. That's a really big result. Thank you for listening.
I became too nervous that I forgot. Now, we'll have a brief discussion with our secretariat about the presentation we heard a moment ago, with the main topic, how can quasi-crystalline structures be utilized to improve the performance of energy storage devices and batteries? 정민, 채원, 원정, Bear consists Team A, while Tae, Minsa, and Eugene are in charge of Team B. To begin with, I will ask speakers in each team to deliver their opinion in approximately 3 minutes. I propose to hold your questions until each member has spoken so that they can have their full time allotment. Then we will have some back and forth time discussing and answering questions. Let's begin with Jungmin Kim.
Have you all been listening to our presentation? Now we will hear from 2 teams, A and B, about the topic, how can we utilize quasi-crystal structure to enhance the performance of energy storage device and batteries. First, our team A will present our opinion, focusing on superconductors.
We believe that to enhance the performance of energy storage devices and batteries, utilizing quasi-crystalline structures in superconductors is a good idea. One primary reason is to consider the improvements in electrical conductivity. Quasi-crystalline structures can enhance the electrical transmission speed and improve overall power efficiency.
In addition, we can also take low-temperature superconductors as an example. By applying quasi-crystalline structures to superconductors that typically operate at low temperatures, we can make them available at higher temperatures, reducing cooling costs and technical difficulties.
Now, if there are any questions regarding our opinions, please feel free to ask.
Thank you for your insightful perspective. I'm curious about how the safety of superconductors with quasi-crystalline structures is being evaluated.
Quasi-crystalline materials, thanks to their high active surface area, can enhance the cycle stability, which in turn can improve the safety of superconductors.
In that case, what role does the technology of superconductors utilizing quasi-crystalline structures play in the development of green energy and carbon neutrality?
As mentioned earlier, by utilizing quasi-crystalline structures, we can adjust the electronic structure and enhance the characteristics of the constituent materials, ultimately improving energy efficiency.
Thanks for the reply.
Next, we will continue with Team B's opinion of quasi-crystal structure with hydrogen storage systems.
We believe that to enhance the performance of energy storage devices and batteries, utilizing quasi-crystalline structures in hydrogen storage systems is a great approach. When quasi-crystalline structures are used in hydrogen storage systems, they make the absorption and release of hydrogen molecules easier.
Additionally, hydrogen storage systems utilizing quasi-crystalline structures have relatively low manufacturing costs and can offer cost effectiveness when applied in the market.
Now, if there are any questions, please feel free to ask.
Thank you for the insightful opinions. Hydrogen is a high-pressure gas with explosion risk. Can the use of quasi-crystalline structures resolve the safety issues?
Utilizing quasi-crystalline structure in hydrogen storage systems can enhance safety. Therefore, the system can operate reliably over an extended period and remain useful for a longer duration.
I'm curious about the development in hydrogen storage technology using quasi-crystalline structures. Are there any innovative research or technology trend?
Research on metal hydrides are being conducted. Recent research focuses on improving the performance of metal hydrides by using new alloys and nanotechnology, expanding the possibilities for hydrogen storage and utilization.
Thank you for the information.
We have heard the opinions from both sides. Team A suggested using quasi-crystal structure in superconductors, while Team B recommended their application in hydrogen storage systems.
Well, super and excellent ideas, and I hope everyone here will have time to consider which approach will be the most efficient. With that, we will conclude this discussion. Thank you for listening.
Our next speaker is Suji and Jiu K, speaking about possibilities to mathematically quantify the future value of a business or investment. It is known as a systematic approach to quantify the expenses and gains of business alternatives. Let's hear about the representative methods of this analysis.
Hello everyone, I'm Sujin Lee and
Jiu Choi.
today we'll conduct a presentation about cost-benefit analysis and its application. These are the contents we prepared. First, we'll talk about the definition of cost-benefit analysis. Then we'll move on to the net present value, in short NPV method, and the internal rate of return, in short IRR method. The former one is used mainly when we compare alternatives with different scales, and the later one is method frequently used for comparing several alternatives in a single group.
What is cost-benefit analysis? It is a systematic approach to quantify and monetize the expenses and gains of business alternatives for determining the feasibility of each alternative. There are two representative methods. First is the NPV method, and the second is the IRR method. With a decrease of monetary value over time, present investment brings more profit than future investment. Under the premise that future profit has less economic value than present profit, we adjust the expenses and gains of the future expenses into present value of currency. This process is called discount in mathematics. Please be aware that the discount here is not saying saving or discounting the money of the price, but here it indicates arranging future price into present value of currency. It is intended to qualify the present and future economic situation and to determine the investment value.
Now we'll talk about the NPV method, which is comparing the economical efficiency of alternatives through subtracting present value of long investments from total present value of cash flows for benefits. The formula above expresses the division of benefit and cost by a discount rate for a certain period of time. In addition, B stands for benefit, C for cost, R for ratio of discount, J for time period. Using this method, there are two cases where we adopt an alternative in a business situation. One is when given a single alternative. If the result of present value of benefit minus present value of cost is greater than or equals to 0, then the alternative is considered economically efficient. In other words, the alternative has investment value. Then you should have an inquiry about the reason. NPV equals 0 case also has the potential of being accepted, while the result equals to 0 would also be considered an economically efficient alternative. That's because a lot of workforce and commodities are required for operating a business, and therefore positive economic effects, including employment effect and consumption of raw materials, are created. NPV is similar to break-even analysis, which is comparing the cost of investment and the benefit from the output. In break-even analysis, when calculated net present value becomes 0, that is where the break-even point is made. In this graph on the right, when section A is equal to section B, that's where break-even point appears. On the other hand, given a single alternative, it is economically efficient when benefit-cost ratio becomes greater than 1.
Now we'll move on to the IRR method. To vividly understand it, let's first take a look at this graph. In the graph, point P refers to the moment where present value of cash flow for future benefit minus present value of cash flow for future cost becomes 0. As a result, the right side starting from point P indicates that business enters financially profitable condition. With that in mind, we can understand that discount at point P can be interpreted as the minimum discount for business to have economic viability. Therefore, the IRR method is defined as applying the comparison between discount at point P and the market discount rate on the judgment of the economic efficiency of alternatives. This is the formula for the IRR method. It is intended to calculate the internal rate R, let me rephrase myself, the internal rate I, and by comparing the internal rate of several equations and several alternatives, the decision makers can verify the economic viability. For a reference, B stands for benefit, C for cost, I for internal rate, and J for time period. When using the IRR method, there are two representative situations that you have to consider. First is when given a single alternative. If the IRR of business itself is greater than the market discount rate, then the business has high visibility. Second is when given mutually exclusive alternatives. This can also be referred to multiple alternatives given with different IRR. So in this case, business that has high IRR of business itself than market discount rate is economically efficient. To illustrate the second case, please take a look at this chart. In the chart, if market interest rate is 9%, then business A, B, and C has investment value. However, if interest rate cut happens because of interest rate fluctuation, the business with low IRR also gets profitability. In this case, we can say that additional investment occurs. So if market interest rate drops to 6%, for example, then business D also has the investment value. To conclude, mathematical calculation of various economic values can be leading the logical decision-making process that leads to many social occasions that we can integrate through mathematics. So from this analysis and these proofs that we see over here, we can see that we can analyze various social values through mathematical solutions and logics.
Thank you for listening.
Next, we have Kim Ji-young, An Seon, and Lee Soo-min with us to give us speech about AI, neural network, and activation functions. Please give a big welcome.
Hello, I'm Ji-young Kim
서연아,
and Soo-min Lee, who represent AI neural network functions and mathematics. Today, our content is CNN active function, loss function, gradient descent, backpropagation, and vanishing gradient problem.
CNN stands for Deep Neural Network, which is an artificial neural network composed of multiple hidden layers between the input layer and the output layer. In deep neural network, structures per object identification models, each object can be represented in a hierarchical calculations of image-based elements. CNN was first introduced to process images more effectively by applying filtering techniques to artificial neural networks, and later a term of CNN currently used in deep learning was proposed. The basic concept of CNN is to automatically allow each element of the filter represented as a matrix to be learned to show data processing. CNN is configured to apply filtering techniques to the original image and then perform classification operations on the filtered images by adding a new layer called the compilation layer and the pooling layer before the fully connected layer as shown in figure 3. The compilation layer performs various functions such as pooling filtering techniques to the images, and the pooling layer reduces the size of the images by converting the local parts of the images into one represent scalar value. A compilation layer has as many filters as the number of channels of the input image, and the output image of the compilation layer is created by applying a filter assigned to each channel.
Images generated by CNN via non-linear activity functions such as convolution layer and LELU are entered into the pooling layer, and the pooling layer is primarily implemented basis the mask pooling. The convolution layer is the most important component in CNN, and unlike the fully connected layer, maintains the shape of the input data. The three-dimensional image is received in the input layer as shown below, and the output is also outputted as three-dimensional data and transferred to the next layer. Because neurons in the convolution layer are only connected to pixels in the relation area of neurons in the convolution layer rather than other pixels in the input images as shown below, we focus on the low-level properties in the previous convolution layer and we combine them with high-level properties in the convolutional layer. The first problem with FNN when processing images is that the correlation between different pixels is ignored. Since the FNN receives data represented in vector form, the image must be vectorized as shown as in figure 9. However, image data typically have very high correlation between neighboring pixels, resulting in huge information loss during the vectorization images CNN. CNN, on the other hand, receives data in matrix form to preserve the image's shape, thereby preventing information loss in the process of vectorizing the image. An active function is the natural network circuit that determines whether or not to send input values of one node to the next. Active functions are characterized mainly by non-linear functions because they reduce the meaning of different layers when linear functions are used. Active function types include step function, sigmoid function, hybrid tangent function, and LELU.
The next topic is the loss function. A loss function is a function that measures the difference between a given input data and the model's predicted results. The loss function measures how well the model performs during the running and adjusts weights and biases to minimize errors. In addition, the loss function can be customized for different types of problems. This allows us to adapt the loss function to the problem for the best performance. The example is mean squared error. This means the mean of the square of the difference between the measured or predicted value and the value considered true. The closer you predict, the smaller the error value and the smaller the mean squared error. The next topic is the gradient descent. The gradient descent is a method of finding a variable values with minimum values of functions by transforming variable values in the direction of lowering function values. Here is how to derive the gradient descent. First, find the least square error. The least square error is the least squares of errors and can be summarized in the following way. Let's leave this expression number 1 and move on to the next process. You can first differentiate the equation we saw earlier with respect to b. If you do partial differentiation, you get the following equation. Third, we divide both sides by n. So as you can see, we have an equation for b. Next, we are going to derive an equation for a. The first equation we looked at is differentiated for a. In the previous equation, we looked at what equation the character b can be represented by. And from the equation that we just derived, we were able to see the letter b. If so, just substituting the letter b into the expression leads to the following expression. Finally, we develop an equation for a and eliminate the same character. Then you will also know the equation for a. This is all about proving the slope descent method. So far, we have looked at the formula for inducing slope descent. So, what does the sign and magnitude of the slope mean? A positive slope means that the larger the x value, the larger the function value. A large slope also means that the position of x is far from the x coordinate corresponding to the minimum maximum value.
Gradient descent has the advantage of being easy to implement because it is a simple and intuitive algorithm. But there are definitely downsides to this descent method. The first drawback is step size. Step size is used to move variables in the slope descent method. If the step size is too large, the distance to travel once increases, so it may converge. On the other hand, if the step size is too small, it may not radiate, but disadvantage is that the speed decreases and the time it takes to derive is longer. The next disadvantage is local minimum. Graphs do not always have one extreme speed value. In this case, you may fall into the wrong place and fail to derive a global minimum. A similar example is a plateau phenomenon. As you can see in the picture below, the slope converges to zero and it stops no minimum at all the way. And the last disadvantage is the increase in the number of operations. The gradient descent has a limitation in that you have to calculate the slope one by one. Therefore, there is a disadvantage that a DNN with many nodes to calculate requires a large number of operations.
Have you ever heard of backpropagation? The term backpropagation means algorithms used primarily in multi-perceptual neural network learning. It can be compared with the term forward propagation, which is used to calculate from the input layer to the output layer, then output the result. If you can guess from the name, backpropagation is basically the opposite. It is used to calculate weights by reversing the calculation from the output layer to the input layer. So how did backpropagation appear in algorithms? I'll explain a short background of the appearance. The traditional slope descent method updates weights using a slope, and updating all weights on multiple layers one by one requires a lot of computation and memory, which is very time-consuming in algorithms. So comes the advent of backpropagation to solve such problems. Let's take a look at the features. First, the initial weight values are given randomly, with each node being considered a perceptron. Then the out value is used in the calculation of the next layer, and the last out becomes the output. This is the reason why the sigmoid function is used as the activation function in backpropagation. However, the method using gradients shows a vanishing gradient, which is a major problem in algorithms. So what exactly is a vanishing gradient problem? It is a phenomenon in which the gradient value becomes very small as you move away from the output layer during the backpropagation process. Please take a look at these two graphs of sigmoid and hyperbolic tangent function. As you can see, the differential graph of the sigmoid function shows the maximum slope of 0.25 and the minimum converges to 0. It has a value between 0 and 0.25, and since the slope is less than 1, the value becomes smaller as you multiply, with no change in the weight, and the error value does not decrease any further. Hyperbolic tangent function was proposed as one of the methods to improve the limitations to the sigmoid function. Unlike the sigmoid function, the hyperbolic tangent function doubles the range of output values so that the output values fall between the maximum and minimum. However, hyperbolic tangent function also has difficulty preventing the gradient loss problem because the gradient size decreases significantly as the value becomes smaller or larger. The ReLU function has been proposed as an activation function that solves the vanishing gradient problem. The ReLU function uses a new activation function, and it returns 0 if the output value is less than 0 and returns itself if the input value is greater than 0. The ReLU function has a lot of advantages, and one of them is that its learning is faster than the other activation functions, and the gradient vanishing problem does not occur when using ReLU function. It also prevents the gradient from becoming 0, which slows down algorithm learning, and the weight update speed is very fast. Because of these advantages, the ReLU function is the most commonly used activation function. The ReLU function, however, does also have some limitations as well. If you can see in this graph, it shows the dying ReLU problem where some neurons in a DNN are deactivated and the output becomes 0 with nothing being changed. There does exist an alternative and a solution to this problem, and it is to use the leaky ReLU problem. However, due to time constraints, I hope to tell you more about it if I get the chance. Thank you.
After many interesting speeches by present speakers, you must be a little bit tired. However, I'm sure that Eun-So-ju, Seak Kim, and Jimin Park are just the appropriate speakers to finish today's wonderful speeches. They will give a speech about Schrödinger's wave equation. Please welcome our last speakers with a round of applause.
Hello, I'm Eun-So-ju. I'm Jimin Park.
And Seak Kim.
Today we are going to introducing about Schrödinger's equation. Before knowing about Schrödinger equation, we have to understand about quantum mechanics. So what is quantum mechanics? The quantum mechanics is, according to quantum mechanics, events that occur in microscopic worlds that can only be calculated probabilistically until they are observed, and that there are possible states of coexistence. So the famous example is Schrödinger's cat. Ever been near heart? So this experiment is, we put cat and poison in the box, and in the box there are 50% of die or life. So if we wouldn't look at in the box, we can know cat is die or life. So we call this state death and life are overlapped. So this is very important clue to connect macro world and micro worlds. So now we have to introducing our Schrödinger's equation. Schrödinger equation refers to the energy state of a quantum such as an electron expressed as a wave function when treated as a wave. So now we are going to inducement.
So before explaining Schrödinger's equation, we have to know three preconditions. First, exponential function. When we differentiate or interpolate this function, we can get the same result with original function, so we can calculate function easily. Second, Euler's formula makes trigonometric function and exponential functions calculate simple. And thirdly, wave function can be expressed in this way. Now I'm going to explain inducement of Schrödinger's equation. First of all, we need to understand the momentum and energy of photons before to start the derivation process. As you learn in the curriculum, the momentum and energy of photons can be expressed in this way. And as we've just explained, the wave function can be expressed with trigonometric function and E. If we differentiate this function with t and x, we can get this equation and we can multiply this value to make it easier to organize them. And finally, we end up with this formula. Now we'll transform the momentum and energy of the photon that we obtain. What we can see here is that momentum and energy can be correspond to this equation respectively. On the other hand, energy can be expressed as the sum of kinetic energy and potential energy, and can be expressed using momentum in this way. If you substitute the corresponding value of momentum and energy into this equation, you can organize it like this. In other words, this value is the total mechanical energy, which is called the Hamiltonian in terms of another operator. From this expression, we can multiply directly by psi on both sides and let it appear as follows. Now, if we come back and summarize the k and w of the wave function in terms of momentum and energy, you can get the following equation. And we can differentiate this function 1 time for t and 2 times for x, and then rearrange E as follows. Finally, if we summarize all the formulas we have obtained before, we conclude that E psi equals to Hamiltonian psi.
We know that Schrödinger equation explains the wave of particles, right? Okay, from now on, I will talk about equation's physical meaning. First of all, we need to know that the square of a wave function means the probability of finding an electron. Please take a look at this graph. This graph's x-axis means the distance from the center of the hydrogen atom, and y-axis is the square of the wave function, that is, the probability of finding an electron. The graph on a hydrogen atom's 1s orbital is drawn like this. It means the probability density is highest in the center. And on 2s orbital, the probability density is highest in the center, and 0 part appears and exists again. Based on these graphs, an electron cloud could be drawn like this. We can think about Schrödinger's equation for the hydrogen atom that has one atomic nucleus and its solution. First, we have to put potential energy of electrons in the hydrogen atoms into equation. And we can express the solution with multiplication of function for distance r and function for angle theta and pi. This function looks like this. Next, what is quantum numbers and what does each mean? Principal quantum number we call n indicates the discontinuous energy value of the electrons in the atom. Azimuthal quantum number we call L determines the angular momentum of an electron, and that determines the shape of the orbital. Last, magnetic quantum number we call M is z-axis component of angular momentum. As variable MLM change, the probability density function changes. Finally, we can see how the orbital model was derived.
Next, I'm going to introduce the Schrödinger equation applied to modern physics. Originally, Schrödinger equation is a priori equation like Newton's equation. However, based on the history of physics, it can be inferred when a particle has a property of a wave, there will be wave equation that occupy it. If a particle with a mass of m moves in one dimension under the influence of positive energy Vx, Schrödinger equation follow this expression. So we have Schrödinger equation matched with its dimension. We have one dimensions, second dimensions, and third dimensions. Next, there are three conditions that a wave function should have. First, function must be finite. So this say that the function should not be disconnected. Second, the function has a single value. That is no more than one wave function in equal to one value of x. Third, the wave function must be continuous for all regions. It should not be disconnected. The value of the wave function must also be continuous. No place where the slope changes continuously. When the graph is clear, like this picture, the slope of the point changes continuously. For free-moving particles, the Broglie relationship can be derived from the Schrödinger's equation, and it is possible to express kinetic energy equation for existing particles zero momentum. Because these two equations are semantically consistent, we can derive the Broglie relational expressions. Thank you for listening to our presentation.
Now for today's last activity, we will solve quizzes about the three presentations we have just heard. If you know the answer, raise your hand please and wait until you get the microphone. And once you get the microphone, please say your name and the answer. Let's dive right into the question about the first presentation.
Our first question is about translational symmetry. I'll read out three materials and you need to tell me which one does not have translational symmetry. The options are first salt, second diamond, third glass.
One.
Please say your name.
Come Kim.
One is correct.
Good guess.
Three glass.
Please speak your name.
서진 Kim.
The correct answer is glass. Glass is an amorphous material and generally does not have translational symmetry. The molecular structure of glass is not regular. Molecules are arranged in disorder.
Moving on to our second question, we're exploring the properties of quasi-crystalline structures. You need to identify which statement is not a property of quasicrystals. The options are here.
Is it the second one? It has rotational symmetry. Well, I can't tell. I just feel like it's just intuitive thing.
Incorrect. Over there. Say your name first, please. I don't think so. Over there, I can't remember who raised her hand first.
Ellie Kim 2.
I'll count to three. Put your hand down, please. I'll count to three, and then you may raise your hand. 1, 2, 3. Back.
Swincho 1 is answer.
Yeah, correct. The answer is 1. Polycrystallines doesn't have spatial periodicity.
From now on, questions are about the second speech, specifically financial analysis. In the world of financial analysis, there are two main methods for evaluating the worth of an investment. Can you name these two methods?
SEAKIM and NPV and IRR.
It's the correct answer.
Our next quiz is a yes or no question. NPV is an important concept in calculating investment.
Anyone else? You already said something, so only 2 options. Just guess.
차력손 X.
Incorrect. Put your hand down, and she'll count to 3.
1, 2, 3.
Okay.
Wrong.
영서.
You have to win me, okay? Rock, scissors, paper. Rock, scissors, paper. Rock, scissors, paper. You two do the rock, scissors, paper.
Correct. Now let's move on to the last question about the third speech. AI neural networks functions at math. What is the most important factor in CNN, the process of maintaining the shape of the input data and receiving, printing, and delivering the 3D image to the input layer?
Use choice, convolution layer.
Oh, correct.
Oh, this is the end of our quiz. I hope you all enjoyed and had a meaningful time. Thanks for your participation. As we draw the symposium to a close, I want to extend our heartfelt gratitude to all the moderators and attendees for making this event a tremendous success. The dedication and enthusiasm exhibited today are a testament to our shared passion for mathematics.
As we end this symposium, we hope the knowledge and the inspiration gained here will lead to our academic and professional endeavors. Let the discussion, insights, and connections today build on a brighter future in mathematical science.
We thank you all for your active participation, and may the pursuit of knowledge through math and science be a rewarding and fulfilling journey for us all. Farewell, and until we meet again on the path of mathematical exploration. Thank you.